One of the important applications of the dot product is using it to find the projection vectors. I will show you how to do that in a minute, but let's consider what is the projection vector is and what does that mean to find it. So let's consider two vectors, A and B, that have the same initial point. So this is a vector A, this one is a vector B, and it's PQ, and this one is R. So, and let's consider the perpendicular that comes out of the point R onto the vector B, of vector A. And let's mark the bottom of that perpendicular by the S. The vector that we get on the bottom here, the part of the A, right, can be considered as the shadow of vector B onto A, is a projection vector that we're looking for. So PS is a projection vector, and it's marked as a projection of B onto A. Projection of B onto A. I want to point out to the fact that it is a vector, all right? So whenever you're finding projection vector, you actually finding a vector. Looking at the triangle RPS, we can say that there is a way to find the length of the segment PS, right? In order to do that, we can use the angle theta in between the vectors A and B, and we can write that the length of PS, let me mark it as just the magnitude of PS, is equal to magnitude of B times the cosine of angle between them. This quantity is denoted as comp B onto A, and is called the scalar component or scalar projection of the vector. It's a component. Scalar component, or we also call it scalar projection. Scalar projection of B onto A. I want to point out to the fact that the comp BA is a scalar, is a number, while projection here is a vector. Now, let's see if we can get better expression for comp B on A. But before that, I would like to mention one interesting thing. So if the angle theta is between 0 and pi over 2, I'm sorry, then the projection vector here is, the component of the projection is positive. While when theta is between pi over 2 and pi, then the component is negative. So finding it, be a little bit careful with the sign of the component of B onto A. Now, let's see if we can get better expression for the component. So component is magnitude of B cosine theta. We know that the cosine can be expressed using the dot product. Let's replace the cosine with the dot product of two vectors, A and B, divided by the product of their magnitudes. And now canceling out these expressions, we get that the component is equal to the dot product of vectors A and B divided by the magnitude of the vector A. So now you do not have to know the angle between the vectors to find the component, right? Or the scalar projection of the vector B onto A. Now, what about the vector itself? In order to find the vector itself, we're going to use the idea that the projection vector is equal to the component multiplied by the unit vector on the direction of A. All right, let's see what is that. So the component is A dot producted by B over the magnitude of A. While in order to find the unit vector in the direction of A, we just divide A by the magnitude of A. That means that the projection vector B onto A can be found as the A dot product with B over the magnitude of A squared times the vector A. Thinking about the first part here, the first factor here, it is actually a scalar because the dot product is scalar divided by scalar. You're going to get a scalar, and the scalar is multiplied by the vector A. And that means that you are either stretching or shrinking vector A in its direction to get the projection vector. Now, pay attention to the fact that if this scalar number, this scalar is negative, then the projection vector that you're going to get is going to be the vector that has the opposite direction to the vector A. If the number is positive, then projection vector is going to have the same direction as the vector A. Let's consider an example. Find the scalar projection and the vector projection of the vector B, which is 1, 1, 2, onto negative 2, 3, and 1. We will start with the component, with scalar projection, to see how it works. So it is equal to, again, let me write the expression for the component of B onto A. That is the scalar product of A times, the dot product of A times B over magnitude of A. And that is equal to negative 2, 3, 1 dot producted with 1, 1, 2 and divided by the square root of negative 2 squared, 3 squared, and 1 squared. That is, if you do the calculations, that's going to be negative. Okay, so it's going to be negative 2 plus, okay, negative 2 plus 3 plus 2, or the square root of 14, which is going to be just 3 over the square root of 14. In order to find the projection, you can use the formula that we just got, but you can also use the idea that the projection is the component multiplied by the unit vector in the direction of A. So let's do the second one because we have calculated it already, times the unit vector, so A over the magnitude of A. That is equal to 3 over the square root of 14 times the vector A is negative 2, 3, 1 over, and the magnitude of A is square root of 14 again. So that is going to be equal to 3 14s times negative 2, 3, 1, which is equal to, now we do multiply 3/14 by each component, so you get -3/7, 9/14, and 3/14 for the projection vector.